Hey everybody, welcome back to Dave's Math Channel. I'm your host David Tare, and I decided to start a new series, and this is a series of videos I'm making on algebraic number theory. This is a particular area of number theory. As a matter of fact, it's an area that it's my main field of expertise in math because I have a PhD in algebraic number theory. Um, so anyway, and if you're curious about what this picture is on this cover slide, this is a picture of some small ordered pairs of integers, x comma y, that are relatively prime. It turns out that the asymptotic fraction of such pairs of integers that are relatively prime is 6 over pi squared. You can prove this using algebraic number theory. Anyway, that's a little bit of a complicated problem. I'll start with some much easier ones in this series. But today I just want to introduce the topic of algebraic number theory. I'm not going to actually go over any particular problems today. I'll just kind of give you an overview of what the subject's about. So, before we delve into algebraic number theory, it's a good idea to answer what number theory is. I have several other videos on this channel on number theory. And I even have one where I think I define number theory, but I might as well do it here as well. So number theory is the branch of math concerning properties of numbers. As you might expect, that's how it got its name. But more specifically, at least traditionally, it involves integers and rational numbers. And the origin of number theory starts with, we can trace it back to an ancient Greek mathematician named Diophantus. He lived in the 3rd century AD, and he was known for coming up with some interesting problems whose solutions were integers. I think all the ones he had were integers, usually natural numbers or positive integers, because I don't think Greeks even knew about negative numbers. But I think they also involved some problems with rational numbers, fractions. I think the Greeks did know about fractions, but they didn't know about negative numbers or even zero. So the original, the original number theory problems, also known as Diophantine equations, involved the solutions were always natural numbers or maybe fractions, also called rational numbers. But then, as you all know, I think by the 16th century, first by about maybe in the West, by the beginning of the 13th century, the West had zero. That was actually invented a long time before in India. The Indians knew about zero, I think, right around the time of Christ, and I think the Arabs knew about it shortly afterwards, but it didn't come to the Western world till around 1200 AD. I think Fibonacci was one of the first people to introduce zero. And um, Anyway, so then we have zero, negative numbers. We can easily extend the notion of Diophantine equations to integers, positive or negative, or fractions that are also positive or negative. So that's kind of in a nutshell what number theory is about. It's how to solve problems whose solutions are integers or rational numbers. There's some problems that were very, very difficult to solve, especially at the time of Diophantus. I think for a long time, probably for several centuries throughout the Middle Ages, probably even in the early Renaissance, I think what mathematicians were trying to do to solve these Diophantine equations, they were just kind of using trial and error, seeing what worked and what didn't work. And I guess if they were lucky, they were able to solve some of these equations, but they didn't really have a method. Number theory is a branch of mathematics started much later, and I think one of the pioneers of number theory there were a couple big ones. I think Euler and Gauss were probably the two biggest sort of modern number theorists. Descartes maybe also, but there and then there were different types of techniques that were used to solve different kinds of Diophantine equations that led to different branches of number theory. And the simplest branch of number theory is elementary number theory. That's what people were using ever since Diophantus. That's just kind of trial and error, seeing what works. And, elementary number theory is still a field today. As a matter of fact, I think Paul Erdos is known as probably the greatest elementary number theorist in the world. He wrote something like 1,500 paid papers and came up with about 1,000 conjectures about um, number theory, most of which are still unsolved. But he was able to solve a lot of them using elementary techniques. So we can't dismiss elementary number theory. But then we also have more sophisticated methods. We have analytic number theory. This uses properties of analysis. A good example of that involves the Riemann zeta function. There's some pretty amazing analytic functions that actually shed a lot of light on properties of numbers, rational numbers, integers, prime numbers in particular. Riemann zeta function is a really amazing example of that. It's an analytic function. I'm not even going to go into what that is, but it's a complex valued function whose roots tell you a lot of really important information about prime numbers. Pretty amazing thing. But that's analytic number theory, and there's a lot of other applications of analytic number theory as well. But then the one I'm going to be talking about is algebraic number theory. Uses properties of analysis of algebra, abstract algebra, to solve properties of numbers, integers, and rational numbers. And I'll get into what that is in a minute. But then there's another field, another very important and probably the newest field of number theory, and that's what's called computational number theory. And this, as the name implies, uses algorithms, computer algorithms. It's kind of the branch of number theory that's involved in what kind of computer programs can we write to find properties or solve problems, Diophantine equations, or problems involving integers, usually really large integers or really complicated fractions. So that's a very important field as well. And also a fair amount of computational number theory because my thesis advisor, Hendrik Lenstra, that was his field of expertise. Even though he was my thesis advisor for algebraic number theory, his main field of expertise was computational number theory. And there's a lot of crossovers of these branches of number theory. I mean, there's computational algebraic number theory. As a matter of fact, there's a very good Springer book called An Introduction to Computational Algebraic Number Theory, one of my favorite Springer books. Springer books are very, very complicated, by the way. Most of them are graduate level, and most of them are over my head. But I do have the Introduction to Computational Algebraic Number Theory at home. It's an excellent book. I've gone through parts of it. Um, and you should beware of the titles that start an introduction to. One thing I've found is that most of the texts I've seen in math or in science, if they say an introduction to so and so, it means they're horribly complicated. So don't be fooled by the title "An Introduction to." Those are some of the most difficult texts there are. Just to warn you guys. Anyway, let's delve into algebraic number theory now. This is the main thing I want to talk about. That's what this whole series is going to be devoted to. So, like I said, algebraic number theory is a sub branch of number theory that uses techniques from abstract algebra to solve Diophantine equations. And um, it also, and another interesting thing about all these branches of number theory, even though they all started out as just ways to solve Diophantine equations, which are equations involving, integers or rational numbers. A lot of them kind of grew into fields about extensions of integers and rational numbers, kind of abstract fields. And there's some areas of number theory where don't even look like you're studying numbers at all. You're studying all these really high level abstract concepts. That's kind of how they developed. And I guess algebraic number theory is an example of that. I mean, we can extend the notion of rational numbers, integers to rational numbers, but then we can go beyond rational numbers, what we call algebraic numbers. And I'd say that algebraic number theory is really more about algebraic numbers than it is about integers and rational numbers. I mean, you can often use it to solve problems involving integers or rational numbers, but there's also a lot of really interesting problems just concerning algebraic numbers themselves. So I think now I have to define algebraic numbers. And an algebraic number is really, it's a real number, or it could be complex. It's a complex number that's equal to a root of a polynomial with all integer coefficients. That's how we define algebraic numbers. And a simple example of that are square roots. Uh, for instance, square root of 2. That's probably the simplest irrational square root there is. That's just the root, it's the positive root of the quadratic polynomial x squared minus 2. I think you guys all know that x equals square root of 2 means x squared equals 2, or equivalently, x squared minus 2 is 0. So when we say it's a root of x squared minus 2, we're really just saying roots are sometimes called zeros. So it's just a solution to the equation x squared minus 2 equals 0. And there's actually two of them. One's the positive square root of 2, the other's the negative square root of 2. Square roots always come in pairs, one positive, one negative. And one thing you should know about square roots, I don't know how many of you guys know about complex numbers. Probably most of you. I have a bunch of videos on this channel on complex numbers, but you can have square roots of negative numbers as well. As a matter of fact, the square root of -1 is known as I. That's the imaginary unit or the imaginary constant. And in general, you can have square roots of negative integers like square root of -5. That's just I times the square root of 5. So you might as well use negative as well as positive numbers and integers inside your square root, and those are just as real. I mean, you name imaginary numbers a little bit unfortunate. Imaginary numbers are really just as real numbers, and people use them all the time in math. I guess we call them imaginary because we don't usually experience them in the real world, but they do exist, and they even exist in physics and quantum mechanics. Quantum mechanics requires their existence. But I'm getting a little sidetracked here. So those are some simple examples of algebraic numbers, square roots. But we can go beyond square roots. We can do cube roots, fourth roots, nth roots. Those are still algebraic numbers. I mean, like the cube root of 2 would just be a root of the equation x cubed minus 2 equals 0. And you can have very complicated algebraic. You can have very complicated rational expressions. These are also called solvable algebraic numbers. Solvable because they're solvable in terms of radicals. And you can have some very complicated rational expressions like the cube root of the fraction 2 plus square root of 6 over 5. That's just an example I came up with. Those are solvable, but then it turns out there's also algebraic numbers that are not solvable. They're called unsolvable. I think this was proven by Abel in the early 19th century. There are, in particular, degree 5. It turns out that every polynomial of degree up to 4, all the roots of such polynomials are solvable. They can all be solved in terms of radical expressions, but in general, degree 5 or higher are not solvable. So here's an example: the polynomial x to the fifth minus x minus 1. That has a positive real root, but it's not solvable. It's algebraic, but it's not solvable. We can't write it as a radical expression. And there's other numbers that aren't even algebraic. I mean, like I said, algebraic numbers of roots of polynomials with integer coefficients, but there's other real numbers. I'm sure you guys all know some of them, like pi and e, and natural logarithms. None of these numbers are algebraic. You can't write them as roots of polynomials with integer coefficients. Took a long time to prove that. I think pi wasn't even known to be, these are called transcendental numbers, by the way. So real numbers that are not algebraic are known as transcendental numbers. And pi and e and natural log or 2 are some examples of transcendental numbers. But those aren't really part of the domain of algebraic number theory. Anyway, so you might wonder, well, what is this good for? I mean, what kind of problems can we solve in algebraic number theory? Well, there are tons of them, and here I just list four. Four of the most commonly, I guess there's four of the most basic ones. You guys probably know about Pythagorean triples. A Pythagorean triple is just a triple of integers a, b, c, where a squared plus b squared equals c squared. They're named after Pythagoras, who supposedly proved the Pythagorean theorem. I think it was actually proven way before him, but he got credit for it. He did prove it. I don't think he was the first to prove it, but so we know that a squared plus b squared equals c squared whenever you have a right triangle with legs of length a and b and a hypotenuse of length c. So these Pythagorean triples correspond to sides of a right triangle. You have a right triangle with integer sides, and you might wonder, for what integers does this work? What triples of numbers are Pythagorean triples? And it turns out we can use algebraic number theory to find all of them. We can actually use it's pretty easy to do it using algebraic number theory. I don't think you have to use algebraic number theory. There are other ways to do. I think you can do it using elementary number theory actually, but it's a lot easier and it's a lot more straightforward if you use algebraic number theory to find all Pythagorean triples classifiable. And then another good example is Pell's equation. This is a very badly named equation, by the way. It was named after a mathematician named John Pell, I believe. He was an English mathematician. He had practically no bearing on this equation at all. This is probably the worst named equation, mathematical result I know, because this was a much older equation. He was even solved a long time before. I think it was solved by a German mathematician. I don't even remember his name, but I think it was solved in the 18th century. And then Pell was in the 19th century. I guess they still didn't know how to solve it in England yet. So what Pell did was he found this paper by this German mathematician. He translated it into English. That's all he did. He just translated this problem whose solution was already known in English, and he got credit for it. Go figure. But often life works like that. People get credit for the wrong things. But I just thought I'd mention that. And anyway, what is Pell's equation? Pell's equation is the Diophantine equation: x squared minus ny squared equals 1, where n is an arbitrary non-square positive integer. It can't be a perfect square like 1, 4, 9, 16. It turns out if n is a perfect square, there's no solution to this equation. But if n is not a square, like if n is 2 or 3 or 5 or 6 or 7, most positive integers aren't perfect squares, as you probably know. If it's not a perfect square, it turns out that this equation has infinitely many solutions. And you can find them all. You can find them all pretty easily using algebraic number theory. That's another good example. And then the number 3 is one I really like. Representing integers as a sum of a certain number of squares, and it turns out there's the number of squares is important. It turns out let's look at n equals 4 first. So suppose you want to know how to represent a given positive integer as a sum of 4 squares. Well, it turns out that here's an interesting result. I think it was Laplace who proved this in the 18th century. I think it was Laplace, maybe Lagrange. I can't remember who did it, but some famous it might have even been Euler. I can't remember who did it. But in the 18th century, there was a famous mathematician who proved that every positive integer can be represented as a sum of at most 4 squares. You never need more than 4. And there's even a formula that tells you how many possible ways there are to do this. Pretty remarkable. And you can derive this formula using algebraic number theory. It's difficult, but you can do it. I learned how to do it a long time ago. It's not an easy problem, but an easier problem would be sums of 2 squares. And with 2 squares, you can't. You can no longer represent every number as a sum of 2 squares. For instance, 7. 7, you can't write 7 as a sum of two squares, but you can write other numbers like 5. 5 is 1 squared plus 2 squared 13 is 2 squared plus 3 squared. You can keep going like that. There's a lot of numbers you can write as a sum of two squares. Well, you can use algebraic number theory to determine exactly which of those numbers you can write, which numbers you can and which one numbers you can't write as a sum of two squares. And you can also determine all possible such representations, including how many there are. So I think that's a pretty neat problem. It's not even that hard to do it using algebraic number theory. I'll probably make a video on that pretty soon. And then finally, I have to mention prime numbers because prime numbers appear all over the place in math, and they're a big focus of number theory. I mean, I think every branch of number theory would not be complete without prime numbers. And I mean, it's funny because a lot of sort of amateur mathematicians, I don't think they really understand why primes are important. But prime numbers are one of the most important concepts in mathematics. And I can tell you right away why primes are so important. Primes are important because they're the building blocks of all integers. I mean, you guys probably know about the fundamental theorem of arithmetic that says that every positive integer has a unique representation up to ordering the factors as a product of prime numbers. Pretty amazing. And so, in that sense, prime numbers are the building blocks. They're like the generator of all integers, not just all integers, but all rational numbers. And you can use algebraic number theory to study prime numbers. You can learn a lot about prime numbers just using algebraic number theory. And not only that, remember how I was mentioning that algebraic number theory isn't really just concerned with integers and rational numbers. Well, you can even extend the notion of prime numbers or primes to other types of number fields. You can talk about prime numbers in algebraic number fields. That's what's kind of neat. You can extend the notion of prime numbers to fields of subfields of complex numbers. We're always dealing with complex numbers. But all algebraic numbers are complex numbers. So you have these fields of algebraic numbers, and you can talk about prime numbers in those fields, and they're not necessarily integers. And I think that's really neat. And anyway, that completes my video for tonight on my introduction to algebraic number theory. Thank you for watching. Long live math, and I'll see you guys next time.